Let's welcome the next speaker for the fourth paper. So is this investigating the effect of misalignment on membership privacy in the white box setting? Please welcome.
Yves-Alexandre Monja. I'm the.
Please welcome Evis and
Cool.
please.
So basically, I'm presenting this work on behalf of my former PhD student, Anna Maria, who can't be here today because she. Oh, sure. Which is a very good reason for not being here. So I'll do my best to do justice to the paper and at least give you a sense of what we've been working on. Because this is a very mixed session, who knows about why, basically membership inference attacks and machine learning models. Okay, so half the room, something like this. Okay, who has already attempted some membership inference attacks on machine learning models? Okay, good, perfect. Just so that I get a sense of what I should spend a bit more time and a bit less time on. Oops, okay, I'm setting the counter. Perfect. That's my usual disclaimer. So basically, the story goes that machine learning models can, and one could argue actually often, are trained on sensitive data sets. And if the model were to leak information in some ways or forms about their training records, right, that might break users' expectations of privacy. And that might potentially, from a legal perspective, means that machine learning models suddenly become personal data. And there's been quite a large range of work and literature in this field, for those of you who don't know the field, in terms of what can be extracted basically from a trained machine learning models, ranging from membership inference attack. We're going to spend more time talking about this today, but also attribute inference attack. So if I know part of your record, can I figure out the rest? Property inference attack, so can I extract information about general information about the data set that was used to train a model. Recent work in correlation inference attacks, so basically does the model somehow remember correlations between the input attributes of a classifier, for example, etc., etc. Membership inference attack are basically the essence is from the trained machine learning model, can I infer whether a specific record was or was not part of the training set of a model. Why do we care? I think mostly two things. First, in some cases, that is a risk in itself, right? So machine learning model can often be trained, especially when you look at specific classes, on data set where membership, right, being in the data set is in itself a sensitive information. Right? And we've already had, when it comes, for example, to location data, to high-profile examples of, cases where membership was, a true concerns. For example, COVID vaccination. We had an example in location data of a priest, basically, that was found and re-identified allegedly in a data set coming from Grindr, et cetera, et cetera. But we also care about membership because, this is kind of the strongest attack, right? The idea is that differential privacy protects against membership, and if you protect membership, then under certain theories of privacy, you protect against everything else. So that's why there is such a big emphasis, in a sense, on membership inference attack from an empirical perspective, an empirical privacy perspective in the field. So how would an MIA work? So basically, the idea is just, given a record, right, can I, with reasonable confidence, infer whether this record was part of the training set or not. And often how they instantiate it is basically, can I train a model? Can I train, for example, a meta-classifier to distinguish between a record that was seen and not seen during training? The issue is that in practice, right, you're very unlikely as an attacker to have this really clean data set of, all of these people have not been seen, all of these people have seen, and this is my model, and just nicely train your meta-classifier on these, and then if I give you yet another one that comes from the same distribution, then you will be able to make some inference. And so what people do in practice is they simulate the behavior of the model in a controlled setup using something called shadow models. So what shadow models are basically is you have the attacker dataset, a dataset that basically you have that looks like the original dataset, and you take this dataset and you draw from this dataset to train what we call shadow models. And basically what you do is that you look at, for every one of those shadow models, how the model behaves when it has seen the record during training, when it has not seen the record during training. So basically, you're artificially building models that look like your target model, but for which you can cleanly control what has been seen and what has not been seen during training, right? And that's basically how you learn and how you train a membership classifier, that then you can apply this membership classifier to the output of your target model with a target record and come up with a probability. Does that, before I go there, does that make sense? Especially for those who do not know membership? Yeah, good? Okay, perfect. In particular, one area of interest for us has been on-device models, right? So there's increasingly a trend, especially in the AI, LLM, computer vision, to move models to the edge, to move models on your device. That reduces latency, that potentially allows you to keep things more private, or at least that's the theory. And we've seen a lot of models from image model for CSAM detection to large language model moving on device. However, from a privacy perspective, that also changes things, right? It basically means that now that it's on device, right, first you can you as the model developer lose control over what I use the model for and how many queries I can send, and often also means that I can recover the actual parameters of the model, right? Meaning that the model is not a black box to me anymore. The model to me is a white box, right? Is I can, once it's on my phone, I don't know, when Apple came up with their CSAM proposal, right, to basically check images using perceptual hashing on device, I think it took people a few days to basically extract the algorithm and be like, hey, so this is the super secret algorithm that they use to try to check if an image is illegal. And so in theory, at least, right, the intuition is that white box should be attacks with white box should be better than attacks with black box, right? You know strictly more, right? You can run everything you run in black box, but on top of this, you have the exact architecture, the model weights, and you can compute everything, right? So from an information theoretic standpoint, you get just a lot more information, and you would expect this to help attacks a lot, right? I should be able to do so much more with white box access. And so typically, right, one thing that people could do is in the white box setting is basically instead of using just the label, right, you could use the output of the model's internal layer as an input to your meta-classifier, right? So you take more information slightly earlier in the pipeline, and you would expect this, in theory, to give you more information, better classification, stronger attack. Which from a privacy perspective also means that if there's any chance that your model is going to be on device, right, what you should protect against from a privacy perspective should be different. However, surprisingly, so far, white box attacks, and there's a range of them, often perform poorly, sometimes worse than black box attack. And when you combine them, and even when you combine them, you usually don't get something that is much better than black box, which is weird, right? It's like literally you have so much more information. You have the exact architecture, the exact weight. You can simulate everything you want. And yet, in so many cases, white box does not perform better than black box. There have been a few work who, have identified this and basically have developed, workarounds, right? So either you remove the need for shadow models, right, and you train directly on the target model, or others have been developing things like proxy models. But fundamentally, there is a question, and this is what we wanted to look at, which is why is that? This makes no sense. I'm giving you strictly more information. Somehow it feels like I should be getting something out of this from an attack perspective. Two? Okay. Sorry, I just need to I have 2 minutes. The issue basically is misalignment. So basically here we trained 5 models using the same layer, the same 4-layer CNN. And basically every time we change different subset, model initialization, ordering of the mini batches. And basically the only thing you should see here is basically that all of the models learn pretty much the same thing, but in different orders. Right? It's the same, they look pretty much the same, but the order is very different. And this is basically because of symmetries in deep neural networks, right? So basically you have, and the main one is probably this permutation equivalent, right? It's like all of the neurons in the hidden layers can basically be switched in order, right? In any ways you want, which give you a very large number of perturbations that give you the same output, the same model, but just with permutations. And the same is true when it comes to CNN with activation maps instead of the neurons. And so basically what we did, 3 things. First, identifying the key cause of misalignment in shadow models. Second, realignment techniques. And 3, given realignment techniques, went back to white box MIA, can we do better? So first, most important cause of misalignments, right? What are the differences? Why are those things not aligned? 3 things. Training data set is different. Model weights might be initialized differently, or you might have some randomness of the training algorithm, ordering of the batches, or some dropout regularization. We basically studied this by varying things, basically varying one at a time. So target models, we change the batch ordering, doesn't change too much. Dropout selection doesn't change too much. Weight initialization, basically you can see that it's more or less the same feature, but in a completely different order. Disjoint data set, same thing, probably a little less aligned, but a lot more than in the weight initialization case. So same features again, broadly aligned, right? Which basically means that the biggest, surprisingly, out of all of those source of variation and those misalignment is basically weight initialization, which is super important. We validate this by using a weight misalignment score. Basically look at the top. This is random perturbation, and this is so much different in this, and then we vary one thing at a time, and basically what you can see is that the biggest source is, again, same story, weight initialization is what changes, particular for the first layer, a bit less for the third one. Okay. I'm being told I need to finish. So basically, we propose a method to realign the layers. We have a range of techniques. 3 to 6 basically works quite well in terms of techniques to realign, knowing where it comes from to realign. We study white box MIA in a range of scenarios, and we show that basically it gives you a much stronger attacker once you realign. So takeaways. First, we study, carefully the phenomenon of why is white box not outperforming black box as everyone would expect. We show that this is due to misalignment. We study what is the main cause of misalignment, and we show this to be weight initialization and not data sets or anything else. That has some pretty strong implications, right? That basically means that if you know the weight initialization, and in particular, if the model was fine-tuned from a base model, you might end up with white box attacks that are much stronger than the black box attack because everything has been already kind of aligned, and whatever you changes afterward is not going to really break those symmetries, making white box much stronger than model trained from scratch, which I think is a really, really key thing. And for those, in cases where adversaries, you deploy it on device, the adversary do not know the weight initialization, you can use realignment technique to improve basically the strength of attack and improve white box MIAs. And the source code is available here. I'm happy to take any question, but basically Anna Maria Cretu, my student, is the brain behind this work, and this is a collaboration between Microsoft and Imperial College. Thank you.
Thank you very much. Are there any questions? There is a question here.
Hi, thank you for the interesting talk. And I might have missed something, but as far as I understand, as far as I understand, typically we use disjoint subsets of the dataset to train the shadow models. And in one of your slides, what you were showing was that they are essentially learning the same, but if we are using disjoint sets or subsets, how can they be learning the same? Theoretically, they should be different. Each shadow model should be different, even though it's from the same domain.
Yeah. So it's really interesting, right? Because it's like basically we know that shadow models are different, right? And I think the go-to is basically to say, well, from a privacy perspective, like, oh, we don't have access to the same data set, and this is where so much of the difference comes from. And there is some difference, right? You can see here, you can see the difference when you have, like disjoint data sets, right? That has an impact on, the alignment, right? And so that means the shadow model are slightly different. But that is actually a much smaller impact than the impact of weight initialization, right? And that fundamentally it's really like you start from think from, again, I come from optimization, right? Think of optimization, it's basically you dropped somewhere in the space randomly and then you find your way towards a good model. And basically what this says is that where you're dropped is actually, will have a dramatic impact on the resulting model. Not necessarily that you learn a different model, but that the alignment is going to be different. As you, again, once you know the answer, it's obvious, but I think it's really important, especially when it comes to fine-tuning, right? Which basically means if I manage to get away and to solve the misalignment issue, which is typically you fine-tune a base model, which by now is a big fraction of the models, then suddenly white box attacks do not suffer from this and might very well become a lot stronger than black box, contrary to everything we thought to be true in older fashioned, not fine-tuned models, which is really cool.
Okay, let's thank our speaker once again. And